Hi everyone, thanks for waiting a while. Now we started. Today we are presenting the boarding the VSAT real-world exploit, testbed validation and policy gap in maritime connectivity, and we are thrilled to be here. Okay, let me kick things off with a recent case. On March 80, 2025, a hacker group called Lab Dookhtegan claimed they launched a massive cyber attack against two major Iran shipping companies. This incident is considered one of the largest maritime cyber attacks, paralyzing the communication network at 116 Iran vessels. Lab Dookhtegan is an Iran anti-government hacking group active since around 2019. In this attack, they exploited vulnerabilities in ships VSAT to not only disrupt ship-to-ship communications, but to completely shut down our external link, including port connections. These incidents really show just how vulnerable ship VSAT systems are, but here's the big questions. First, do VSAT attacks stop at just communication disruption? Second, how far can VSAT vulnerabilities actually reach? Third, how can we stop maritime cyber incidents that are already happening? Before the starting, feel free to ask casual questions anytime, and for technical ones, please use the slide link from the QR code on the screen. Okay, let's get started. Quickly introduce our team. I work on Maritime Cybersecurity Research Engineer at CIDR INC. He is the Juwon, is pursuing his master degree at Yonsei University, and Sungmin Lee is studying at Handong University while conducting cybersecurity research. Our research was conducted under KITRI's Best of Best program, where we participated as the 12th cohort. This is our picture. So, what exactly is VSAT? VSAT is very small aperture terminal. These are small satellite communication terminals widely used not just on ship, but in military and aviation applications too. Modern vessels are developing various remote support solutions and autonomous navigation technologies which require complex data communications. This is why satellite equipment is becoming increasingly critical. VSAT serves several important purposes on ship: safety and security, operation efficiency, crew welfare. What's important is that VSAT equipment is integrated into the GMDSS. This means it becomes critical communication infrastructure for search and rescue operations during accident. Now, let's look at the specific architecture of VSAT systems. VSAT systems have three main components. First is antenna. As we all know, the antenna has three features. Next is the ACU. It's typically a 90-inch leg mount control device that handles antenna control and monitoring functions. It often provides a web interface for remote antenna management. Finally, this is the modem. This is the satellite modem that converts RF signals from the digital data. It supports various protocols like DVB-TEC-S2 and TEC-RC-S2 for maritime application and has integrated TCP/IP acceleration for optimized satellite link performance. But here's the key questions. As a researchers, where should we focus? We choose the AC web interface. Why? First reason is accessibility. Satellite modem use proprietary protocols and complex RF processing but AC web interface use the HTTP and HTTPS. Anyone who gains access to a ship's network can open in it with just browser. It's also a practical attack better. We've actually found AC web interface exposed on the internet, some still using default credentials. Second reason is impact. Compressing an ACU gives for antenna control. That means you can cut off satellite connection or point it to the long satellite. In short, this is a real-risk entry point that attacker inside a ship's network would likely find and their target first. Next is Juwon.
Basic security research is new. Some great work was done before, like the studies from 2013 and 2018 in Black Hat, but since then there's still been a gap. Past research shows possible vulnerabilities, but didn't really dive into real and practical attack scenarios. One of the big reasons is cost. VSAT equipment is very expensive, so testing on real equipment often means breaking the bank. That made deep and hands-on research difficult. Do we really have to spend that much? We find a better way. It's a firmware rehosting. I will explain that in a moment. Our goal was to see if VSAT web interfaces expand online could be used as an entry point for ship in penetration. We started by collecting VSAT firmware through official channels. We select two vendors. Cobham software was used across more than 13 different devices, and we also analyzed Intellion equipment, where we discovered RC vulnerabilities. But unfortunately, we can't disclose the detail of those vulnerabilities here. Early on, we used binwork to quickly check for encryption. This mattered because newly firmware often uses OpenSSL encryption, so that means we didn't need the actual hardware analyze it. Since our goal was to work without real equipment, so we had to exclude encrypted firmware from this study. Now let's work through our firmware rehosting and our analyze and rehosting process. We started with the firmware, used binwork, and quickly found it was ARM-based with a full file system inside. So we moved straight to extraction. Extraction gave us 3 directories. The main one, squishfs root, had the full file system structure. In the boot script, etc/init.d/rcs, we saw it calling another script that set up symbol links and directories for mounting. Following the trail, we found mount appl.sh, which uses su-mount.awk to mount another file system. It's a squishfs root1 to mnt/appl in the main root. This second file system was our goldmine. It contained the web interface code running on a light TPD server. For rehosting, we used ARM-QEMU, forwarded the port to our host PC, and manually mounted squishfs root1. CH rooted into the main root when RCS and started with the web interface binaries. Our result, we had the full ACU management web running locally, like a login, settings, and everything worked perfectly. We found a total 6 vulnerabilities in the web interfaces, all caused by insufficient user input validation. So as in the table, 4 XSS vulnerabilities in the various ACU web settings, and 2 are OS command injection in report functions. The 2 RC cases are particularly interesting. Both occur because user input passed directly into the system function. One in the statistics report feature and one in the diagnostic report features. These issues are based on any complex exploitation. They are actually dangerously easy to trigger. So the next question is, where do we go from here?
All right. Now, let me walk you through our ship testbed construction and attack scenarios. But first, let's talk about how modern vessels are changing. To understand the digitalization trends in modern ships, we visited the Korean Maritime and Ocean University. We toured their remote control and autonomous ship research labs, actually boarded real vessels and spoke with navigators and engineers. We learned hands-on how ECDIS, AIS, and SATCOM and ICS equipment actually operate. Through this journey, we discovered three key changes. First, the network separation between IT and OT infrastructure on ship is becoming blurred. Second, as infrastructure increasingly replace human crew roles, there's much more remote data transmission, makes ships heavily dependent on satellite communication. Finally, Ethernet is now being used for ICS equipment control. This is our testbed that we built to verify the ship cyber attack scenarios. It's composed of 5 levels, ranging from VSAT to network gateway, and PLC and HMI representing the ICS. Finally, we started with Mark 1 to verify that equipment at each level could communicate properly, then moved to installing everything in an actual small rack to complete Mark 2, our full maritime testbed. This is our attack scenario, 6 steps total, and the initial attack surface is the ship's VSAT web interface. From there, we move through network devices to reach the HMI at the bottom layer, manipulate the PLC, and ultimately cause physical damage to the vessel. Step 1 is asynchronous hunting. During our 2023 research, we found many ship VSAT management web interfaces are exposed online, excluding COBAM and intelligence systems. Using Shodan and criminal IP, we collected IP addresses and found 104 ACU web interfaces of COBAM and 14 Intellian. Among these, 25.96% of COBAM systems and 100% of Intellian systems had known vulnerabilities. While the exposure problem has improved since 2023, a significant number of devices are still identifiable of the internet. This is the criminal IP user interface we use. The actual ship, it has an automatic feature that tags them with ship. Once attacker identify ACU web interfaces, there will attempt intrusion. COBAM and many other VSAT manufacturers put default credentials right in their equipment manuals, easily found online. In this case, attackers can simply access the VSAT and try logging with these default credentials. No technical vulnerabilities needed. They get immediately access to sensitive information like satellite configuration, vessel location data, and network topology. So, would simple changing the default credentials make it safe? No. We discovered 6 vulnerabilities in the actual COBAM VSAT management web, and while I can't give specific in this presentation, we also find RC vulnerabilities in Intellian VSAT. When we analyzed the ACU web binary responsible for web execution, we found the sub219C4 function doesn't validate user input and passes it directly to system functions, allowing attackers to execute arbitrary commands. What's notable is how easy this attack is to execute. Attackers can use free proxy tools to attack ship, VSAT, and log in as administrator. This becomes step 3. So now attacker is inside the ship. The attackers use ping or ANSI commands to investigate internal gateways or network devices connected to the VSAT. After this recognizes, they will attempt the lateral movement. We actually purchased a widely used network switches from the market and perform vulnerability analysis on it. Surprisingly, we discovered 4 zero-day vulnerabilities. To verify describe one vulnerability, it allows bypassing administrator login with just manipulated post request. Sadly, we can't reveal the details, but here's the key point. If you can do this, attackers can certainly attack ship network equipment too. Our testbed has an HMI connected to a PLC that controls propulsion via satellite communication. So ultimately, the attacker accesses the HMI through industrial switching hubs below the network equipment. The HMI runs Windows CE operating system, and through the HMI, we could control the project programmed into the PLC. Finally, the attacker can maliciously overwrite or delete PLC projects or unload ransomware disguised as manual PDFs. This could be serious compromising and ship availability and causing physical damage. Now, let me show you a demos. Okay. Yeah, we are currently assessing the rehosted VSAT ACU, ACU web interface on the Raspberry Pi and attempting to log in via SSH. The password is wrong, so we can't connect. But now we are using the vulnerability to change the password to root without authentication. Then we'll see the connecting. Yep, the password is wrong. And now we are connected into the ACU. After gaining the access to the ACU, we check the network with ifconfig commands and can see that .212 and .250 are connected. Since this is an IoT environment, we use ping and ANSI commands for scanning. The IP scanning results shows that .1 and .94 are connected. And port scanning reveals that port 22 is open on .94 and port 80 is open on .1. Yes, this means the port scanning. Now we are setting up port porting so that SSH port 5555 connect to the port 80 on .1. So when we connect to the localhost port 5555, we get the network switch login page. It's a network switch login page. And use the vulnerability of the switch. Now we've successfully logged into the switch using the vulnerability. So our final goal was to verify if we could reach from the ACU all the way down to the Raspberry Pi, acting as OT equipment. As you can see, when we SSH to .94, we successfully got shell. Yep. and this one is a continuous video. This continues from the sorry. Yeah, this one is a continuous video, and we can sorry guys. We demonstrated remotely accessing the HMI and overriding PLC projects to forcibly shut down the connected fan. Right now, we are showing the HMI is configured to run a fan, a small fan, for ship propulsion. When an attacker who has infiltrate the ship access the HMI and override the PLC project, there's no authentication required. So when the device restarts and we press the start button on the HMI, begin operation, as we can see, the fan stops and we can even manipulate the HMI interface itself. Okay. All right. Now is for our conclusion. What we realized throughout this research is that the maritime industry has an enormous amount of paperwork, like IMO, IAX, even ISO, IEC. They are specify every details about ship manufacturing and operation. Certification and regulation are absolutely important. Ships carry many people and directly impact trade, which is a nation economic lifeline. From the perspective of safety and availability, all this documentation make perfect sense. But cybersecurity is a little bit different. Checklist-based security forces us to view ship infrastructure with its vast array of equipment through a narrow lens. IAX Unified Requirements 27 and similar policies requiring security certification for ship equipment are certainly a great start. But considering ship digitalization, we need to move beyond individual equipment security certification to ship-wide threat modeling and penetration testing. Why? Because cyber attacks are systemic. They exploit the interdependencies and cascading vulnerabilities across multiple connected devices. So what we accomplished here? We've demonstrated VSAT firmware rehosting and shown that internal network pivot is possible. We've mapped our attack flows through maritime system architectures, and we've walked you through building a testbed and validating real attack scenarios. Of course, there still remain challenges. Our testbed is simplified, and this is really proof of concept work. Moving forward, we are hoping to partner with actual shipping companies to building a customized testbed that mirror the real equipment on the vessels. That's where we can do proper threat modeling and penetration testing. Maritime security is something we need to take seriously, especially with all this rapid challenges happening. Autonomous ship, new technology everywhere. This isn't just a job for security researchers. We need industry forces, regulators, and everyone working together on this. Okay, that's it for our presentation. You're welcome your question and via Slido or ask directly. Thank you very much. Okay. The materials will be uploaded through the DEFCON archive. Yeah. Thank you.